haven't had a chance to come back from spring break. Hope doesn't meet up on the beach. Right, so we're gonna. So the last lecture, you would have seen thumbnails other than me. I hope you noticed. So that was the last lecture on zero knowledge proofs. You guys saw a zero knowledge proof for tree coloring, which is empty complete, and therefore you have a zero knowledge proof for everything in the world, right? We'll come back to zero knowledge again in a couple of lectures and see its application to other things. But today, in the next 3 lectures, we are going to switch gears, and we are going to talk about a completely different problem, which is remote authentication. So far, more or less everything we talked about had a sort of privacy angle to it. So this is completely right. So authentication. Okay, so here the setting is Alice and Bob. Alice wants to send a message to Bob. Yeah, so we're going back all the way to the second lecture, right? And the question now is not so much whether the Eve in the middle can learn what the message is. So this we sort of know how to solve. If she just sits there and kind of looks at the communication, she doesn't know what the message is. Right? So that's encryption we know to do. Now, Eve tries to modify right? She tries to do things to this, change things going through the channel. Change could be what? Could be, so I could add, so you know, bits to the channel. I could modify the bits going through the channel, right? So generalization add. Or I could delete messages going through the channel. Yes? So there's all these things I can do. And I can do even more sort of crazy things, like I can replay things from the past. Okay, so this is stuff that I know, you know, Alice actually sent, but just not today. I'm gonna replay it. So all these things you can do. Right? So again, you can E can add, delete, modify, replay, all these things. What you want is that Bob actually detects whether a communication is actually coming from Alice or it's being handled. That's the goal, right? So this is what you want. So of course, there's nothing you can do about an Eve that completely deletes all the messages. She just cuts off the channel. What are you going to do, right? So you can't always promise to recover the message that Alice is sending. It's just not possible. But you can at least promise to detect whether, at least promise to not accept messages that Alice did not send. Okay, so that's at least you can expect, and you can promise to do it. That's authentication. That's a problem with authentication. Okay, so we'll sort of start with authentication the same way we started with encryption, the same way we started with privacy. We'll say, let's go back all the way to Shannon-like setting, where Alice and Bob have a secret key. Okay, so they somehow they came together. They agreed on a common secret key, and now Alice wants to keep sending messages to Bob, right? The guarantee is that Bob does not accept a message that Alice did not legitimately send. That's what okay. This is the primitive of MAC, or I suppose message authentication codes. Okay, fair enough. Good. So let's define what that is. So a MAC is again a tuple of algorithms. There's a gen algorithm. There is a MAC algorithm, somewhat confusingly named, and a verified algorithm. Yeah, that's that. What does gen do? Gen is a probabilistic algorithm. So it takes a security parameter. The usual kind of thing that we do is a probabilistic, it's a PPT algorithm that outputs a secret key. Okay, so what is a secret key? This is the algorithm that Alice and Bob run inside a closed room before the beginning of the world. Okay, so they get that check. MAC is an algorithm that takes the secret key and the message and outputs an object called a tag. Okay, so this is something that you need the secret key to produce, and it's tied to the message somehow. It's a tag for the message. This could be either probabilistic or deterministic. There is no real reason to kind of do one versus the other. Rather, there's no real reason to require probabilism, not yet. This outputs a tag. Outputs a tag T. Yeah, so you should think about it this way. Alice is the one that runs the MAC algorithm. She has a message in mind. She has a secret key, of course, that she knows she shares with Bob. She runs something, this algorithm, and it outputs a tag T. Okay? And what Alice sends over is M, T, the message and the tag. Okay, so that's so you do this, M, T is what Alice sends over. Bob, when he gets the message and the tag, has to be able to check, verify using the secret key. He gets M and the tag, and this could either be, again, probabilistic or deterministic, although everything we see today and in class will actually be deterministic algorithm, so you don't need to worry about it. Okay, so this guy says what? Bob says what? He gets a message and a tag, and he has to say, here's a check, I suppose. It says accept or reject. Okay, so it says, do I believe that this is something that Alice really honestly sent or not? Okay, so this is, he says 0 outputs 0 or 1. So this is reject or accept. Right? So this is the interface. So this is the set of algorithms that is right, and you see how these algorithms map to how Alice and Bob would use these. Correctness says that if Alice generated a tag, if they came up with a secret key, Alice generated a tag for a message, Bob would always accept it. Otherwise, it's not very, very good, right? So this you can write down. So again, for every correctness, it says for every secret key generated by Gen, for every message M, for every tag T generated by MAC SK M, if you run verify on SK MET, this says accept or 1. Of course. Yeah. And if it didn't, you'd be in trouble. Yeah. In general, you could say if these algorithms are probabilistic, you could say, look, I don't want this to happen all the time. It can happen. This can happen at 99.99999%. But let's not. Okay. So say I always want correctness. Yeah. That's correctness. That's correctness. Now security. Okay. This is always the interesting part, right? Correctness. Come on. I mean, if you don't know what the correctness is when you're designing the algorithm, you're already in trouble. Okay. Security is it. What does it mean for a MAC scheme to be secure? Okay. So you have to have an adversary in mind, of course, right? You have to decide what the adversary gets. What is the information the adversary gets? Okay, he has to get something. Number one. Number two, you have to decide what the adversary is trying to do to harm you. Okay, number two. What he gets and what he's trying to do. What is his goal? What's his power and what's his goal? Okay. Once you do this, you're still not done. You have to mathematically, you have to turn it into mathematics, but you can do it. Okay, so if you do it 10 times, the last time you can do it. Okay. So the important thing is to understand first of all, what is the adversary trying to do? Okay? What is the adversary trying to do? So the adversary is goal. The adversary is right? Is what? What do you think? Yeah.
To produce a pair MT where Bob accepts, but Alice didn't produce the message.
Didn't produce it. Okay. So you could say fair enough. Yeah. This M could be what? I mean, you think about two different things. Yes. We think about sort of a universal forgery, which says the adversary, I will give him a message, and he will produce a tag that Alice will accept. Okay, universal in the sense he will forge for every message. Okay, so that I'm asking him to do a lot. Okay. Universal forgery. I'm not going to write it up. Eve produces T for every M. For every M that is given, Eve can produce T such that verify accepts. For a randomly chosen S. Okay, so you think about a game, right? I pick a secret key in my head. I give the adversary a message and say, you know what? I wake you up cold, okay, in the morning. Say, give me a time. Yeah, and he has to. I say he succeeds if he succeeds for every time I answer. What you are saying is a notion of existential forgery. Which says he succeeds if she can produce M, T, some message and a tag such that verify accepts, such that this accepts. That's the notion you say. No, of course. Yeah, yes.
Well, can that always be the case? Because you can always, if they happen to guess the secret key, they can just
Good.
find the right tag.
Good. It is. You can do it. If the secret key is 128 bits long, right? It's n bits long. You can do it with probability 1 and 2. So, in other words, I define an event that E succeeds. Yes, it's a probabilistic event. And I want the probability that this event happens to be negligible. Okay, so that's usual. Right? Good. Yeah, so there's a probability that I want, and the probability that E succeeds to be some negligible in the secret parameter. And of course, that has to be the case, right? Because the length of the secret key has to somehow factor into the picture. Otherwise, the length would be 0, and it doesn't make sense. Right? Okay, that makes sense. And in fact, I'm going to insist on existential. I'm going to insist on making the adversary's life as easy as possible. Okay, rather my life as hard as possible. Why? Because I don't know what the adversary is going to do. I mean, he may not. He might succeed if he forges a tag on just one sort of document that says, Vinod pays him, $1 million, and that's, right? I mean, so. Existential forgery is the attack I care about, and a MAC is called existentially unforgeable if this happens. Probability that Eve succeeds in this game. What is the game? I say, Eve, wake up in the morning, give me a message and tag that the verify accepts.
Well, can it be proved that they're equivalent?
No. In the sense. Okay, so exercise. Okay, come up with a MAC scheme that is existentially forgeable, but universally unforgeable. There are good question. So this is the right notion because this is the right notion. Okay, so that's the adversary score. So we've nailed it down pretty quickly, actually. Right? What does the adversary get? What power, what information does she get? So right now I said, wake her up in the morning and say, give me a message and attack. Right? That's not the way the world works.
The message space, the language.
Certainly the message space, for sure. Okay, certainly the message space. Yeah, English. Yeah. One more. Still, I say, well, you know English. Wake up in the morning and say, give me a message and attack. Yes, okay.
Any messages and tags that Alice has ever sent to Bob?
Good. Yeah, Eve is sitting in the channel, right? She's observing stuff going through. What is stuff? Stuff is messages that Alice sends to Bob together with valid tags that Alice could use. She sees all of it. Now she could try to come up with new messages that Alice did not sign together with the tags. Yes? It's a fair game. Okay. Again, here there are two choices, right? So there is a known message. There's a known message attack, which says, Eve does not have any control over the messages that she sees the tag for. She just kind of sees messages drawn from a certain message distribution together with tags. Okay? I'm not going to write it down, okay? Because I don't like it. Yeah. The real, what I want to say is, look again, Alice, in real world, what does she sign? What does she authenticate? I don't know. It depends on whether she's a banker or a professor, okay, or a student, okay? It doesn't. So, I want to give her real power, which is to say, I am going to let Eve ask for tags for messages of her choice. So Eve can obtain tags for messages of her choice. Okay? In other words, the game is the following. Right? I have an Eve. Say, well, I'm going to play a game with you. Okay? So, what is the game? I pick a secret key in my head, and I tell Alice, look, you can give me any message you want. Okay, I'll sign it for you. I'll mark it for you. Okay, I'll produce a tag for you. Go crazy. Okay, as long as you're polynomial time. Okay, I don't care. Yeah, as many polynomial. And eventually, I say, look, okay, Eve says, I've had enough. I have all the information in the world. I am going to now produce a message with a tag. It had better be a new message with a tag. And if she manages to produce this, I say she wins. Okay, so that's the chosen message that I said. Okay. Still not very happy. Okay. She can get tags for, what is she doing? She's making Alice do stuff. Okay, say, hit you with like PDF documents. Okay, Alice, if she's like me, she says she signs everything she gets over email. Okay, yeah, I sign everything. Maybe I shouldn't tell you, but it's that is an attack on Alice. But Bob, the guy sitting there, why don't I attack Bob? Okay, what does it mean attack Bob? I can feed sort of messages and tags, potential tags, right? Feed it to Bob and see if he accepts or rejects. Okay. Of course, I can do that, right? I say, here's the website, get 1,000 Bitcoin for free, okay, together with the signature. Yeah. I show it to Bob. I can see if Bob goes and buys a Porsche or not. Okay, so I know whether he accepts it. So I have access to the verify oracle as well. So I can ask these questions to Bob, can see if he accepts messages and tags. I can ask questions to Alice, give her messages and get the tags. Still, I should not be able to produce a tag for a message that Alice did not sign. That's what I wrote. Does that make sense? So let's make it more clear. Questions? Let's make it precise. So this is a definition of existential. It's a mouthful. Suddenly I'll be tired by the time I write it. Existential unforgeability under a chosen message attack. Or an abbreviated UFA. So the following, every PPT adversary E, right? The probability that E plays the following game. So what does she play? I first pick a secret key out of Jen. Yeah, this is the setup. I give Eve access to the math oracle. The dot means Eve can put stuff, can ask for. This is an oracle that Eve can ask for stuff and will give. And the verify oracle where she can ask for M and T and it will say yes or no. Keeps asking, keep asking, keep asking, right? The probability that Eve produces an M and T such that M is not in the list of queries that to the Mac oracle. Okay? She did not get a tag for this message. And verify MT equals accept. This probability should be negative. It's a compact way of writing it. Really, you should think about it as a game. Game between who and who. There's an adversary, right? Eve. There's a challenger, that is me, right? Challenger C. What does the challenger do? Generate escape. Okay. What can Eve do? She can ask one of two types of queries. She can either say M, and I have to give her a tag. Query type 1. Query type 2, she can give me M and T, and I can say accept or reject. Okay? That's query type 2. She can ask it whatever she wants, interleave, not interleave, up to you. Okay? And a total of following along, arbitrary following along. And eventually she says, look, here is a M, let me say M star and T star. Okay, make this M star and T star. And she wins if M star is not in the list of queries. Okay, so these are both the same thing. An oracle game is the same as an oracle experiment is the same as a game. This is what I want. Good. Any questions? Criticisms? Sure, of course. I gave you for free a pretty strong definition. What are you going to say? Yeah.
Given that interest has to be negligible to decay, does the adversary need access to the verifier to be that strong? Like, in theory, if in polynomial times you get the information that you wanted.
Sorry, again, say again.
So,
your
would the
objection is,
adversary be weaker if it didn't have access to verify? That's all I'm asking. Because of it only needs to produce a good key with negligible probability.
good question. Let me think about it for a second. Yes. So you can come up with a MAC scheme which is secure in this sense, right? But not secure in you're thinking because the verifier produces 0-1 answer, yes? I mean,
Yeah.
come on, like, you know, but you can ask many queries to the verifier.
If he somehow found a way to like get a 1 answer, then I feel like he could have like
Ah.
1 at that point. So like it seems like he's only gonna get 0 answer.
Good question. Good question. Good question. Very good. Okay. So you know what? Your conjecture is that any scheme that is secure in this sense is also secure in this
Yeah.
sense. Okay. Prove it. Yeah.
You just said you had confidence.
Well, I mean, one of us is correct. Very good. So again, the objection, just to make sure everyone understands, is, you know, the adversary poor thing plays the game. Okay, okay. I'm giving it, which means I'm wrong. Okay. Never mind. Okay, so figure it out for yourself. Okay. Sorry. Figure it out for yourself, which is the case. Either the two definitions are equivalent, or there is a scheme that means one of the two is true. Yes. Unless you can come up with a proof online. Why would you think that the two definitions are equivalent? Yes, Arsen.
Well, the argument would be like, if there is a scheme that uses the verifier, it still works.
It is an adversary that uses the verifier to work.
And at some point it either says 0 or it says 1. And if it says 1 on something that's not something like what from non-oracle, it might as well just output it at that point, not send it to the verifier. But I guess maybe it has like a lot of choices. And
So you're going to simulate the verify oracle with zeros. Okay, is it? Well, I mean, either you made a query to the verify oracle, but I have to give you a 1, because you already stopped there. You could have already stopped there and output the VI, right? Okay. Yeah. Go
Oh
ahead.
no, I was thinking if you alternate between like simulating it with zeros and then just like outputting the MT that you would query. So like either like there's gonna be a 1.
Uh-huh.
Like you play this game like many times, right? You only have to win the tag. Like half the times you play with just the map and not the verifier, you simulate. And
You have to win with the somewhat of a quality probability. Yes.
Yeah. So half the time you play with the verifier just outputting zeros, and half the time you actually query the MT that you would.
Offline.
Okay.
Okay. You don't have to think that complicated, I think, but okay. But yeah, very good. Okay, figure it out. No harm, yes? I mean, so now we want to build this this thing. Let's start with the Shannon vault. Okay, what is the Shannon vault? It's a secret key vault, which of course is a vault here, right? And it's a one-time vault. Okay, in other words, Eve can only get a MAC on one message. Okay? In other words, the secret key that Alice and Bob shared, they can use it once. If they use it twice, they're done. Can we do that? Okay, so there's a minimal kind of. Oh, so this you can do. This you can do. And this you can do information theoretically. In other words, I don't need the PPT Eve there. So this is for every Eve. So how do you do it? So one-time max. Good. So here's the idea, okay? Profound idea, right? It'll come up again. If I give you, pick a random line. Okay? I give you 1 point on the line. Can you give me another point? It's up to you, right? If you gave me another point, then you actually knew the line, and and there are, given only 1 point, there are infinitely many lines. In fact, if you have a finite field, there are many lines, characteristic many lines. Rather, the size of the field many lines. Right? This is the idea. That's it. Okay. So what does that mean? The secret key is a pair A comma B in, let's say, for how many CP squared, but it really doesn't matter to be any finite field. In fact, it doesn't even matter that, but we can generalize all sorts of ways with this. Map of message M, you interpret the message as an element in a finite field, element in ZP, is AX plus B over ZP. Yeah. To verify, verify is sort of the canonical verify, yes? I mean, he takes a message and the tag. He knows that the tag is unique given the message and the secret key, so he recomputes the tag and checks if the tags are equal. Okay, that's canonical verify. Okay, check if T equals AX plus B. That's it. Right? Yes. Good. There's no X. Yeah. Very good. Very good. Thanks. Yeah. Good. So, for those of you who know what the universal hash function is, this is that. Two universal hash functions. This is that. And why is it the case that okay? So I claim that there is no adversary E at all, no probabilistic polynomial, anything, that wins in this game except with probability 1 over 3. Why is that? Eve asks for map of the message M. Right? So she doesn't know the secret key. I picked the secret key myself. Okay, she asks for the map of M. What do I tell her? I have to tell her something. Right? I tell her a random number. ZP. Because if I pick A and B randomly, return a random data. So now let me ask you the question. What is the distribution of Mach of M prime? What does this look like? So this is by the way, this is A M plus B for some A and B. Yes? Right. Yeah, I can even pick A and B in my head. Given M and T, right, you have one equation in A and B. Yes? What is Mach of M prime? It's A M prime plus B. Yes? How many possibilities are there for AM prime plus B? It's not true, right? So think of, so you have variables A and B, yes? At this point, what the adversary doesn't know are variables for him, A and B. He gets one equation, which is 1M in a product with AB, or rather the other way around, M1 in a product with A, yes? How many possibilities are there for M prime 1 in a product? So this I told him is T. Yes, I told him is T. How many possibilities are there for M prime in a product? I claim all possibilities. Every number in ZP is a possible solution for M prime 1 in a product AB. Why? Because for any number T prime that I could potentially put in here, there is a unique AB that fits this. Why? Because this guy is a full rank matrix. Okay? As long as M is different from M prime, this is a full rank matrix. Yeah. There you go. So in other words, okay, let's recap. Okay, the marginal distribution of T for Mac of M is uniformly random. That's why I can get away with giving him a random T here. And every possible number T prime is a potential Mac of M prime for a different K. Okay, so different K consistent with T. So the probability that he guesses the right T prime is 1 over B. Does that make sense? Let's see. I have AB in my head, okay? Yeah, I gave you one equation in AB. So this is another way to think about it. One equation in AB. If you produce a MAC for a new message, you would be producing a second equation in AB, right? And therefore you would be getting two equations given only one equation, right? So given one number, one sort of unit of entropy, you can sort of produce two units of entropy. There are many ways to think. Yes?
Can you just guess without knowing the first?
You can guess you will succeed with probability 1 over B. Yes? Yeah, so the point is that given M and T and M prime, different from M, all choices of T prime are possible max. Okay? For different A's and B's, but all possible. So this is sort of like saying in a Shannon setting, right? Given a ciphertext, all possible messages could have been encrypted here for different choices of keys. Yes. In fact, this is a one-time path, if you will. Yes. Very good. So this is a one-time MAC. Is it a two-time MAC? My security proof shows that it isn't, right? If I give you max of two messages M and prime, you can write down these two equations in the secret key variables, and you know the secret key. Therefore, there's absolutely no security. Yeah. Well, can you design a two-time MAC? Can you design a two-time MAC? Yeah, a natural question to answer. I mean, one way to do it is to say, well, you know what? I have two secret keys. Okay, A, B, A prime, B prime. First message I use A. Second message I use A prime, B prime. Not very interesting. Yeah. So we want to move beyond. Now very interesting because why? Because my secret key grows with the number of messages that I want to make. So good thing about it, it's information theoretically secure. Given one equation, there is no possibility in the world that Eve can produce, other than probability, just randomly guessing, she cannot produce the second message of time. Bad thing, it's only one message secure. You've seen this before. One-time path. This is what we saw in one-time path. Yeah? And in fact, if you want this kind of security where Eve can ask for an unbounded polynomial number of max, you can show, well, okay, so you know what? All right, so what would you guess? Can I get an information theoretic many-time MAC? Okay, why do I have the PPT there? I mean, can I basically just remove it and get an Eve that asks many, many, many questions? Okay. Information theoretically secure many-time. Can you get it? History should sort of tell us no. In fact, you can even prove it. Okay, so this could be in your problem set. If it's not in your problem set, you should think about it. Yeah. So, namely, there are no information theoretically secure many time. Okay. This is the analog of Shannon's theorem for max. Yes. Okay. Good. So now you say what? I mean, but we have one-day functions. We have random generators, we have random functions, blah blah blah. Yes. Can you use those things together? That's the question. I'm going to erase this. What would you do? Yeah, so you want a MAC that is secure, even if you get the max on many messages, you shouldn't be able to produce a MAC or any message. What would you? You've already seen laid the groundwork. You need boundary functions. Boundary functions. So how would you use boundary functions? You don't have to use boundary functions per se. You can use anything that can be constructed from boundary functions. For instance, we said pseudorandom generators. We didn't prove it, but we claimed that pseudorandom generators can be constructed from any boundary function. Pseudorandom functions can be constructed from any pseudorandom generator, therefore from any boundary function. All these things can be done. Thoughts? Austin?
The secret key into this energy and get to the random bits, and then those to make as the randomness for the whole time.
Yeah, sure. So I'm complaining that this is only one time secure. How do I make it many times secure? I have 2 copies of the secret key. We have 2 times secure. 3 copies of the 3 times secure. This is too long. The key. But we know how to compress, large random string into a small seed which produces pseudo-random strings. Yeah. But we also saw that this kind of, so what is the problem with doing this, right? So what is the solution again? So we share a seed of a pseudo-random generator. And I keep sort of expanding it, right? So each block is an A, B, and I use it to MAC. And I have to tell you which secret key I'm using at any point. Okay.
So use it to the random function.
Use the pseudo-random function. So this is a problem with synchronization, right? Use the pseudo-random function. Beautiful. Okay, that's it. So the secret key is the seed as key seed or whatever, right? Of a pseudo-random function family. Think of a pseudo-random function family where the functions are indexed by S. Pick a random S. So pick a random key. Function. MAC is simply f sub S of M. That's it. Right. Verify is a canonical verify. Gets a message attack, it recomputes the tag using the secret key and checks if the tags are equal. That's it. This is a canonical verify. I'll just call it a canonical verify. Right, that's it. Why is it secure? I'll leave it to you as an exercise. Okay, this is more or less straightforward. More than less. Okay. It is really straightforward. Right, so we have solved the problem of maths. It was nice to begin with, but we have half a class. It's hard to solve any problem in half a class. So, all right. I'm not happy still. Oh, good. So, this Max actually solved the problems of injecting an Eve that injects messages and Eve that alters messages just natively, right? How about an Eve that removes messages? I mean, he can always remove messages, yes. He can remove all messages. So this has to be handled out of band, right? So something that asks, something that adds sequence numbers to messages. So Alice can add sequence numbers to the messages. And if Bob does not receive, he receives I, sequence number I with a message, and sequence number I plus 1 with a message, he knows something is wrong. Okay, so he can request retransmission. So this is out of band. It's not cryptography, it's something else. Replay is another problem, right? So, Eve should not be able to take a message from, a year ago. Let's say I'll give you 10 bitcoins. When I had 10 bitcoins, right? You should be able to. That again, the way to handle it is to append is to not MAC a message, but MAC a message together with the sequence number, together with the date. So all these things are out of band. We have to be careful. We have to be, MACs don't solve all the problems in the world, but there are these two things, that deletion and replay, that you have to solve all the time. Good, so here's something very important to understand. And we'll get back to this point again and again. Privacy and authentication are completely different goals. There is no way you should sort of confuse one with the other. You should not use an encryption scheme, yes, as an authentication scheme. That should be pretty clear. But again, you can come up with encryption schemes. Well, how would you use an encryption scheme as an authentication scheme, right? I mean, to authenticate a message, to MAC a message, I would encrypt it with my secret key. Okay, to verify, you would decrypt it and you would check that it's completely pointless. In fact, you can come up with encryption schemes where this is a terrible idea. Okay, one-time pass. Okay, just starting from one-time pass. And the other way around, MACs don't do the job of privacy. Although here, this construction actually hides the message, right? So this construction hides the message, yes. This guy does not hide the message in a semantic sense, yes, because if I send the same message twice, I could lose the same tag. So it doesn't, it doesn't hide it. So this is not a good encryption scheme. Encryption schemes are not good MACs. There's no way you should confuse the two. This is like saying P and NP. You should not confuse definitions of P and NP. You should not confuse MACs and authentication and encryption. All right, so these guys again have the problem that these guys only MAC short messages, only messages that are as short as the input for the pseudorandom function, right? So maybe you have pseudorandom functions with a certain input, like 128 bits of input, okay? And you want to MAC a very large file. Okay? How would you do it? Here's one way: break the file into pieces. Okay. So how would you encrypt a very large file? Okay. With an encryption scheme, they can only handle bits. Bit encryption. You break the file into bits. You encrypt one bit at a time. Okay? And it's semantically secure. Okay? How would you MAC authenticate a large file? Of course, you break the file into pieces. You authenticate each one. Concatenate the tags. Okay. Well, that's a horrible idea. You see why?
You could reorder it though.
Of course you could reorder them, right? And here's a new message, which is if I do character by character, of course you can basically create any file you want. Yes, so now good, now very good. We'll get back to this point. Okay, so we need some machinery to do MACs of very large messages. We'll get back to this. Okay, so now, so that's all really about to say about MACs. Let's move on to bits reset. So again, MACs very good, right? I'm very happy. But I'm not happy with MACs for the same reason that I wasn't happy with the symmetric key encryption scheme, which is that Alice and Bob need to go into a room, do stuff, and generate a secret key. Alice is Alice, Bob is Amazon. Okay, talk. Okay, so it's not going to happen. So what I want is a public key version of MACs, which are called digital signatures. MACs is a secret key, object. And the public key equivalent is called digital signature. What does that mean? Since I am extraordinarily lazy, in general and particularly today, context switch. No maps, digital signatures, just a public key. I'll just call it a sign algorithm, but this is the same algorithm, okay? It's the same type of algorithm. Gen is now an algorithm that Alice runs. She produces a public key and a secret key. Public key, I will call it a verification key. What reason? Because it's used for verification. Yeah? So I'll call it, this will output a verification key and a secret key. Alice will publish her verification key in a database, just like she did for some encryption. And she'll keep the secret from herself. Okay, so verification key is public, secret key, signing key, secret key is right. Mac, well, Mac is Mac. I mean, this is a signature algorithm, okay, which takes a secret key and a message and produces a tag T, which I'll call it a signature. Okay, so these are just syntactic changes. The signature, I like Sigma, but it plays the same role as a tag. It is a tag, and it is generated using a secret key and a message. Okay, I just changed a bunch of names. That's all. Verify is still verify. But now the verify can work even if it doesn't know the secret key. Verify is a public algorithm. Anyone in the world can verify, given a message and a signature. Look up, Alice sent me a message and a signature. I go look up her verification key in the sky. Then I say, yeah, I can run the verification. Okay. So again, it outputs 0 or 1. And correctness is precisely the same thing. Okay, so I'm not going to rewrite this, but it is. It's what it is. Honestly generated signatures are always acceptable. That's it. Okay? Make sense? And how would you? Okay, so again, you can ask this question. So what is the good thing about digital signatures? Right, Amazon can go in and say, look, here is Amazon's verification key. Okay, so it is up in the sky. It is in a database. In practice, you have to implement this database as a public key infrastructure. Never mind. Okay, so think about this as sitting in the sky. Okay, verification. Amazon, verification key for Amazon. I go to Amazon's website. It shows me this website stuff. Okay, together with a signature. What do? My browser does. It goes, fetches Amazon's verification, or it has Amazon's verification key in its head. It preloaded it. Why? Because I shopped so much. Yes, it's preloaded. Yeah, so it can check. That's what. In practice, it's a bit more complicated because who says that this database what is up in the sky? It is stored in some place. Yes. Who says that this thing up in the sky is untampered? Yeah, so one way I can sort of kill the whole system is I can go to this website, go to this sort of server that stores this database and say, Amazon verification key. By the way, I'm going to replace the verification key by something I generated. Okay? And now I am Amazon. So you have to maintain the authenticity of that object, that database. That's a separate, altogether separate problem. But we're doing mathematics, right? Yeah, so this is mathematics. To take it to practice, you need to do more things. Good. Let's do mathematics. Digital signature. Okay, good. So, yeah, how would I build a digital signature scheme? And again, here's a theorem that is not hard to prove. There are no information theoretically secure digital signature schemes. That doesn't exist. Even one key. Why? Can anyone think about yeah? The adversary gets a verification key. Of course he gets a verification key because everyone in the world gets a verification key. I want to say that no unbounded adversary can produce a message together with a signature that verifies. Why not? I need one-way functions. That's what I say. Okay, and one-way functions are good enough. It turns out that we'll get to later. But for the what? Okay, I have to tell you what a security definition is. Yeah. The security definition is, by the way, called precisely the same thing. Okay, existential unforgeability and untrustworthy message attack. What is the definition? You challenge the adversary. Okay, so generate a secret key and a verification key. Okay, give the adversary the verification key. Poor guy. Okay, so he knows Amazon's verification key. Okay, Eve knows Amazon's verification. She can query the signing oracle on any message that she wants and get the signature. Yeah. She can also query the verify oracle, now public verify oracle, but she doesn't need to query a verify oracle. She can do it herself. Okay, there's no need to do this. Okay. And then she produces a message and a signature. This is just a syntactic change. T, sigma, who cares? Okay. Such that this message was not queried, she did not get a signature for this message, and yet this is a good signature. Okay? This she should not be able to do. That's the security. So you see, nothing really changed. But the most important is that she got the verification. She can do the verification any number of times all by herself. You can again think about this as a game, so on and so forth. There is no two. That's that. Right. Now let's see. So how would I do it? I would go through the same stuff again. Instead of constructing a one-time act, so let's say I construct a one-time signature scheme. Okay, that's a minimal thing. Meaning, the adversary only gets a signature of one message, okay, and her goal is to produce a signature of a different message. That's her goal. And she should not be able to do it. That's my goal. Right? Very good. Very good. How would I do it? This time, let's say you only have a one-way function. Okay, you don't even have PR. Of course, you can build a PR from a one-way function. So say you have a one-way function. Here's how I'm going to do it. This is called Lampworth's. Referred to as Lampworth's signature scheme. From 19 something, Stone Age. Renaissance. How does it work? The verification, the secret key, let's say I know the length of the message. Okay, the length of the message is L. My secret key is numbers x10, x11, x20, x21, etc., 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 xl0, xl1. What are these numbers? These are numbers that come from a domain of a certain one-way function. So I say, at the beginning of the world, I assume that there is a one-way function. It has a certain domain, it has a certain range. Right? The secret key is a bunch of pairs of numbers from the domain of the one-way function. That's it. What is the verification key? This is a one-way function applied to each of these guys, etc. Yes, that's it. What is the signature of a message? And I said before that M is L bits. Okay, at most L bits. Okay, it's less than L bits pattern. Okay. Signature using the secret key. What would it be? Can you fill it in? anything that happened more than 40 years ago should be semi-obvious, which is again a very inflammatory statement. But this one, you know, what would you do? I mean, like, you can add stuff, but come on, it doesn't make any sense. Yeah.
Do you do the AB thing? So like x10 times the first bit of n plus x11, and then for each of those.
I see. Okay, good. Okay, but what is it? You're right. Very good. But
Dot product?
very good. But n is 1 bit. Yes, that's so. So you said.
N is 1 bit.
No, sure, but can you say it in simpler terms?
M
What
times
is
SK?
m times
SK.
sk?
Oh, like M1.
Oh, I see what you're. M times sk should probably work too. But let's keep things. No algebra, okay? So I don't let you do
Yeah, it
algebra.
works at least when n is random, is what you'd say, right? So you want to appeal to go right level.
Yeah, possibly. Well, because if m is all zeros, then it's. Anyway, doesn't matter. These are all contentless, right? So no algebra, okay? So x is a string. It doesn't have any algebraic structure. What do you do? You just artificially tie your hands, yes? But my point is that there is something completely simple. Just completely simple. I mean, if there's no algebra, I can't manipulate these guys. Yes? These are boxes, and they're like strings. What can I do with them? I can output them. It's one thing I can do. Here is the signature, okay? X sub 1, comma M1. M1 is the first bit. So M, write M as M1, M2, up to ML. Each one is a bit. It's 0, 1. Comma, X sub 2, M2, which is sort of what you said. It's M1 times X11 plus X10, something like that. Yeah, but right? Yes, so on and so forth. XL. That's a signature. Verification. Well, certainly you cannot recompute the signature and check. It's not an option anymore because it only has a verification key. Sigma, this whole thing is sigma, right? What does it do?
Just computes the one-way function for each of the
One-way function on each of these pieces and checks if it is equal to the right piece in the verification key. So check. So right sigma again is x1, x2 up to xl. Check that f of xi equals y, or rather the verification key sub I comma mi for all I. Okay, so right. That's it. Does it make sense what's going on here? Yes.
So, but in like the adversary case of this, the adversary is given the verifier key. So if they see like a message, couldn't they
Message together the signature, I assume.
message together with like the signature? Like couldn't they start like figuring out like enough of the secret key to maybe send like a message?
Let me ask you the following question. Okay. Tell me a message. 0, 0, 0, 1, 1, 1, 1. Okay, so I give you the x11, x21, x31, so on and so forth. You tell me that you can produce a signature of a different message. Yeah, produce a different message together with the signature. What is your message? I don't know. Maybe change one bit. Okay? I mean, you want to keep as many of these things equal as possible, right? Let's change one bit. It's 0, 1, 1, 1. By the way, you know most of the signature, yes? They just kind of write. But there's one component of the signature that you don't know, and to figure it out, from the verification key, you need to invert the one-way function. That's the point. Right? Good. And this can be turned into a. So this, right. But you know what? Is it 2 times secure? Okay, I let you now, you know what? Ask 2 queries. Okay. What are the queries you will ask? Someone can tell me.
All the 0 bits and all the 1 bits.
Yeah, 0, 0, 0, message 1. 1, 1, 1, message 1. I just gave you the entire secret key, now you can do whatever you want. Okay. So it's 2 times insecure in any sense you want. So the question is, how are we going to make this, I claim that there is a signature scheme that is many times secure in that sense, given perhaps not in this class. How do we go about doing this? Let me set up some machinery today, and then we'll sort of continue with the next class. Okay. The very first question I want to ask is, well, this guy only lets me sign a message of length L. 1 time, never mind, but let's stick with 1 time for a moment. Okay, so let's say the adversary only gets a signature once. But I want that to be a long message. Okay. I want this scheme to be able to sign very long messages. How do I do it? Okay, good. So this we need some machinery. And that's a primitive called collision resistant hashing. Collision. Yeah, collision resistant hashing. What is a collision resistant hash function? It's a family of functions H, just families of little h's. Each little h maps from 0, 1 star to 0, 1 to the L, right? Such that, well, first of all, each h, little h, should be polynomial time computable. Polynomial in what? In the intellect. Okay, so such that A, each h is poly time computable, and B, it has to be collision resistant. Okay, so what does that mean? There are collisions in this function, okay, because it maps everything to L bits, right? So pigeonhole says there are collisions, but no polynomial time adversary should be able to find even a single collision. That's what the so for every PPT adversary A, here's the game. A gets a function H. What is H? H is drawn at random from the family capital H. The probability that he produces xy such that x is different from y and h of x equals h of y should be negligible in the security parameter. This way. Makes sense what I'm saying? There's an implicit security parameter here. This is really a family, family of families, where each family is indexed by the security parameter. Then I say, well, I have to first pick a large security parameter. That tells me a family. Now I pick a random function from this family. And roughly speaking, the description, the number of functions in this family should be 2 to the power of the security parameter. Yeah, so these are functions that shrink, they compress. Therefore, there are collisions, but no polynomial time adversary can find. That's what that is. And given a collision-resistant hash family, I claim that you can make this into a one-time signature, which can sign arbitrarily long messages. then I'll show how to construct a collision resistant hash family. Because, yeah. So let's see why it's useful. So again, this is a one-time signature that can sign long messages. Okay, so what is it? SK, same as before. BK, same as before. No change. Signature, well, something has to change, right? Now it gets a message M with a single P, and the message M could be very long. Okay. The verification is key is the same comma H. H drawn. Okay. The obvious thing to do is to sign a message, a very long message, first hash it to L bits, then run the old signing algorithm. Let's say M prime, 1, M prime is the hash of M, H of M, right? The verification key also has the H, let's say. The secret key also has the H. 2, old signing algorithm, Lamport signing algorithm with M prime after that. Yes, so now, yeah, long message, first hash it down, take the L bits, now run Lamport. How does the verification algorithm work? It gets this long message together with the signature. It says, well, let me also hash it down. Okay, now I get a little bit message. Now check, run the Lamport check. That's what. Is it clear? This is called the hash and sign paradigm. Okay. Why is this secure? Still in a one-time sense, because we're not using anything more than one-time signature scheme as underlying primitive. Still, I want to claim that this is a one-time secure signature scheme. So again, you play the game, you give me a very long message, I first hash it and run Lamport, I give you the signature. Now you claim that you come up with a different message and a signature on that. Okay? I claim that's not possible. Polynomial time algorithms cannot do it. Why? Yes. Awesome.
You will either break the thing you used before or break the
Collision resistance, right? The new message that you gave me either hashes to the same L bits, right? In which case you broke collision resistance, or it hashes to a different L bits, in which case you managed to sign Lamport with 2 different L bit strings. There. Does it make sense? Now all that remains, so the theorem is one-way functions plus collision resistance functions give you a one-time signature scheme which can sign a arbitrarily long messages. It's still one time. Good. So now, I want to sort of take a tangent, I suppose, and show you a construction of collision resistant hash functions. Okay. So let me show you. At least I'll start today. Here is a collision resistant hash family. And this will be collision resistant under the discrete log assumption. Okay? It's not under one-way functions. In fact, I don't know how to construct collision resistant hashing from one-way functions. Yeah. Discrete log. Okay, then, yeah. So, even to get one-time signatures for many, I'm not telling you how to do it for one-way functions, although we know. Okay, so here is the hash family. Each hash function here is parameterized by, it's parameterized by a group P, right? ZP, G1 and G2. Yes? And this guy is going to map not 0, 1 star to a small string, but a string of length twice something to a string of length something. So it's going to shrink by a factor of 2. Then we'll show how to take anything that shrinks by a factor of 2, or in fact, even by 1 bit, and make it shrink by, any number of bits you want. Okay, this is generic transformation. But let's shrink by a little bit. Okay, factor of 2. This maps from ZP squared to ZP. Rather, P is a So how does this work? So I'm going to drop the P from here. So H sub G1, G2, it takes 2 elements, x1, x2, in ZP minus 1, in the exponent group, right? 2 elements, x1, x2. And it does the following. It computes G1 to the x1 times G2 to the x2. Again, 1. Therefore, it maps to ZP. This is what it does. Okay? So it takes 2 elements in ZP minus 1, essentially 2 log 3 bits, and maps it into log 3 bits. So it shrinks by a factor of 2, more or less, except for the timing. Okay? This is the family of functions. And I claim that if I give you a random function from the family, you won't be able to find 2 inputs, x1, x2, and x1 prime, x2 prime, that hash to the same thing. Unless you break discrete log. Rather, if you do it, I'll use you to break discrete log. Good. That's it. Now let's see the proof in 2 minutes. So this is what I want. How do you prove it? I pick random G1, G2, give it to you. This is a hash function. You come up with, so say A given G1, G2 outputs a collision which is x1, x2 different from x1 prime, x2 prime, such that the hashes are the same. Okay? Namely, let's write it down. G1 to the x1, G2 to the x2 equals G1 to the x1 prime, G2 to the x2 prime. Okay. I claim that from this I can solve discrete log. What does it mean solve discrete log? Discrete log of what to the base what? Okay. I mean, really are multiple things here. So you have 2 choices. It doesn't matter what you pick. G2 to the base G1. Okay, that's it. That's what I'm going to extract from this. How? Let's say for a moment that G2 is G1 to the power Z. Say, okay, Z I don't know. I'm going to try to extract it. So what does this tell you? G1 to the x1. Yes? G2 to the x2 is G1 to the power zx2 times G1 to the power zx2. But hey, you know what? This means these guys add up. Yeah? Equal to G1 to the x1 prime plus zx2 prime. Yes? Yeah, might be. Now what? This means that x1 plus zx2 is equal to x1 prime plus zx2 prime, 1p minus 1. And this is an equation in Z. You
Since you're solving this mod P minus 1,
Yeah,
which is like
indeed,
not prime.
I just saw this, yeah. You're saying x2 minus x2 prime could be actually not relatively prime to p minus 1. Therefore,
Yeah.
you can't invert it. True. I just saw this. Let's take it offline. Okay. You can still solve this in a subgroup, but let's take it offline. Okay. So this is what it is. Modulo, what's your name?
Rogers?
Rogers. Objection. We'll continue.